So the approach we're going to take to studying electric forces is that we're going to start with the electric potential, phi. You can think of this as being kind of similar to potential energy. It's the potential energy per unit charge. We'll spend a couple of episodes looking at how we study the electric potential, because once we understand that, getting the electric field and the electric force is just a couple of math steps away. Once we have an electric potential phi, we can get our electric field E just by taking the gradient of phi. So we look at the hilliness of phi, take the negative of that, so that electric field points downhill. Wherever the electric potential goes downhill, that's the direction that the electric field is going to point. And then to get the force, we just place a charge inside the electric field. The force that charge experiences is just its charge value times the electric field. So once you know phi, once you can get phi, the electric field and the electric force just a couple of mathematical steps away. So the electric potential is governed by something called Poissons Equation. The idea behind Poisson's equation is that you have the electric potential phi here. You're taking the Laplacian of it, and we're going to say that that's equal to negative of the charge density divided by this constant epsilon naught. So let's take a look at this equation piece by piece. This is the thing that's going to walk us through the next several videos in the series. So we'll take a look at this by thinking of it in terms of Cartesian coordinates. So we're imagining that we've got our x and y axes, just like you traditionally have. And then in this region, we've got some charge. So let's say you've got, a blob of charge somewhere. Maybe there's a lot of charge in the center. Maybe there's not as much charge on the outside of the blob. And then maybe there's a point where there's zero charge. Maybe the charge cuts off at some wall somewhere. So the way that this is mapped is with this function rho. So this rho is your charge density. It's your charge per volume at each point. So each point in here, inside this region, is going to have a specified value of rho. It's going to have some value of rho. Again, maybe rho is higher on the middle and then it decreases. You could also have positive charges mixed with negative charges. So maybe you've got a blob of negative charge out here. So inside the red blob, you would have positive charge. You would have rho equal to a positive number. Inside the green blob, you would have negative charge. You would have negative value. And then in the space in between, you might have zero. So this rho can go from negative to zero to positive. The other thing we have to have true about this charge is that it has to be stationary. So this is what we call electrostatics. So the charge is not moving around. So wherever our charge blobs are, they're glued in place. We can deal with moving charges, but then we start to get magnetic fields, so we'll look at that later on. Epsilon naught here is just a universal constant. It's the same everywhere in the universe. It basically takes care of the units. It tells us how strong a particular charge is in the universe. We're going to make this easy in our code. We're going to set this equal to 1. So we're just picking units where this is magically equal to 1. It just makes it gives us one fewer things to have to worry about in the code. You'll notice there's a negative sign over here. We'll talk about that in a second. Over here is our electric potential. Again, this is the thing we're trying to solve for, right? So we want to solve for phi as a function of x and y. So we're looking to get a value for phi everywhere inside the region that we're interested in. Now, that makes it a problem, right? Because phi is underneath this derivative here, right? So if we had phi, we could really easily solve for rho because we would just take a few derivatives of phi and end up with rho. But that's not the way the universe works. The universe presents to you a charge density and then produces an electric field from that. So this is the cause on this side. And this is the effect over here. So that's the direction we have to go with. This upside down triangle, this is our Laplacian operator. So as a reminder, it looks like two derivatives with respect to x and two derivatives with respect to y. And if you worked in 3 dimensions, it would be two derivatives with respect to z. We're going to stick with just x and y for now, just to keep it simple. So this is a multi-dimensional version of the second derivative. It basically tells you the curvature of the of the electric potential at any given point. The Laplacian is written in terms of partial derivatives instead of full derivatives. There's really no technical difference between the two. A derivative still works the same way. This is just a little notation to help us keep track of the fact that x and y are independent variables. You're only going to be varying one of them at a time. That's actually going to be important in a few minutes when we get to approximating these things using slopes. So if you remember that the second derivative of a function, because that's what we're looking at here, we're looking at del squared of phi is going to be second derivative of phi with respect to x plus the second derivative of phi with respect to y. If you remember, the second derivative gives you an idea of the concavity of a function, right? So when you have a maximum in your function, that's when you're going to have a second derivative that is negative, and when you have a minimum in your function, that means your second derivative is going to be positive, right? And so the fact that this has a derivative with respect to x and a derivative with respect to y, instead of just having a maximum like this, you can kind of imagine it being rotated around. It means you have a hill or you have a valley. That's essentially what that means. So if we read this just qualitatively without getting into any numbers or functions or anything, the second derivative of phi has to go like the opposite of whatever the charge density does. Okay, so let's think of that in terms of our diagram here. So in this red blob, we have a whole bunch of positive charge here. Okay, so rho in this region is positive. We're taking negative rho, right? So negative rho here means this whole thing is going to be a negative number, which means our second derivative is going to be negative. So you look over at your key here. A negative second derivative means you're in the area of a maximum. So somewhere in here, in wherever the charge is the highest, is going to have your phi at a maximum. So a positive charge produces a hill for the electric potential. Let's read it again for the negative charge. So let's suppose we make rho a negative number. We have a negative times a negative. That makes this whole side positive. So that means our second derivative of phi is positive. Well, a positive second derivative means you're at a minimum. So wherever you have a negative charge, you're going to be at phi equals a minimum. And so wherever you put charge, right, because we're in charge of where the charge goes. And so wherever we place positive charge, we'll be creating a maximum in phi. Wherever we place negative charge, we'll be creating a minimum in phi. And basically, Poisson's equation just tells you what happens in between, right? It tells you how you go from a maximum to a minimum. It tells you how the slope is going to behave at each point in between where you have positive charge and where you have negative charge. And that's what we're looking to visualize with our code in today's video. So to recap, in an electrostatics problem, you start with a charge distribution. You start out with an area of positive charge, an area of negative charge. Again, those can go anywhere you want. And then Poisson's equation says that the second derivative of phi is going to be given by this rho. And so our goal is to go from the cause, the rho here, to the effect, the phi here. Now, of course, there's a major problem to solving this because our output, the thing we're interested in, the thing we're trying to solve for, is hidden behind two derivatives, right? And so we're trying to undo a derivative, which is kind of like integration, and you know by now that not every integral can be solved. In fact, the majority of integrals can't be solved, and the majority of problems that you put in here can't be solved exactly. And so we're going to use a method called finite differences. And our goal is going to be to transform this equation, transform Poisson's equation, into something that we can put into the computer. And so what I want to review for this video is how we make this transformation, how we turn this from a mathematical equation that we dream about solving to a discrete equation that the computer can work with. Now, I've shown this process in detail in some other tutorial series. If you'd like more information, you can check them out at a link in the description below. But our first step is going to be to take our region here, right? So we're going to be interested in a square region, okay? And we're going to say that this goes from, let's say, L to negative L on both the X and the Y. So we'll go from negative L to L up here. And what we're going to do, we're going to turn this into a grid or a mesh. So we want to take our x and y. So x and y are normally thought of as continuous variables. We want to turn this into discrete variables along a grid. Let me show you what this means. So along the x-axis, we want to imagine setting up little grid marks along here. Right? So instead of having a continuous variable x, we're going to turn it into an x that has an integer label. So I here is just going to be your label for x. Right? That's all it's going to be. And it's just going to count 0, 1, 2, 3, etc. So we're going to start with an I equal to 0, 1, 2, 3, etc. So each one of these little points that we're looking at, each one of these little divisions along the x-axis, we're going to label with an integer I. They're going to be separated by a distance dx. So the distance between here and here is dx. The distance between here and here is dx. The distance between here and here is dx. So our step size, or our grid spacing, it's sometimes called, we're going to call that dx. Right? That's just going to harken back to our derivatives over here. It's going to make it easier to map that out. Then we want to do the same thing with y. So we want to take our y-axis and divide it into evenly spaced intervals. Now here's the thing. X and y, they have to be independent variables, right? Because these are partial derivatives, we have to be able to vary x and vary y separately. So I need to be able to change x while keeping y constant. I need to be able to change y while keeping x constant. And the way we're going to do that, we're going to turn y into another discrete variable. All I have to do is give it a different label. So j here is going to be my label for my y value. So I'll start down here and I'll have j equals 0, 1, 2, 3, 4, etc. all the way up. Right? And what that does, because I've divided up the x's and because I've divided up the y's, I've now really got this thing divided up as a grid. So I divide up the x's and I can divide up the y's. What that really gives me is a grid, right? And so each point in this grid, in fact, that would be at the intersection, wouldn't it? Excuse me. So each point in this grid is at a point xi, comma, yj. And for y, I can use a different step size if I want to. I think I'll probably just use the same one for this code. So we're just going to use the same step size. So it's going to be called dx. You could make it different if you wanted to. Like maybe you're looking at a really thin rectangle instead of a nice square. There's really no reason not to for the problems we'll be looking at. So we're just going to use the same step size there. So each one of these points on the grid basically gets labeled by an address of I, comma, j. So you can think of each point along the grid as just having a different set of labels, I and j. And that's going to tell you where you are in the grid. This is important because this is how the computer can keep track of data, right? A computer can't keep track of an infinite number of values between negative L and L, right? It can't keep track of continuous variables, but it can keep track of discrete variables. So basically what we're setting up here is a data array where we have two different indices, where we've got an index I and an index j. And if you're not accustomed to putting a little curve on your I, now is a good time to practice that because that's the only way you can tell an I apart from a j, unfortunately. So again, I and j have to be different numbers. They have to work independently because x and y have to be independent. Okay, that's what happens to x and y. The next step is look at what happens to our function phi. Right? So our phi, remember, this is a function of x and y, right? Phi has a different value. It's got a unique value at each point in the grid. So at each point in the square here that we're dividing up into a grid, phi can have a different value. That means instead of having one index, phi needs to have two indices, right? Because phi, right, x and y, x can only go along this way, y can only go along this way, but phi can go anywhere, right? I need to be able to have a different value of phi at each location in the grid. So instead of just having an I or a j, I need to have both. I need to have an I and a j. And basically this phi ij is just going to be phi at x equals xi and y equals yj. Right? So we're just taking the grid we made for x and y, and we're just kind of slapping it onto the phi here. So phi, the function, gets replaced by a 2-index thing, phi of I and j. The same thing, by the way, happens to rho, right? Because this charge density over here, the cause, the source of our problem, it's a function of x and y. So you can do the same thing. You can just tack on an I here, tack on a j here. So your rho has 2 indices, rho of I comma j. Right? And so that's how the computer can keep track of both of these. It can keep track of all the values of rho at each point in the grid, and it can keep track of all the values of phi at each point in the grid. Now we have to start thinking about what happens to these derivatives, right? Because Poisson's equation involves phi, it involves rho, but it involves derivatives of phi. So this is where we have to kind of work our way backwards, right? When you first studied calculus, you were really proud of the day when you went from slopes to derivatives, and you stopped worrying about delta y over delta x, and you started worrying about dy dx. Well, now we kind of have to go backwards. So we're going to transform this thing. We're going to transform each of these back into a slope. So let's start with the first derivative. Let's suppose I want to take partial of phi with respect to x. So let's think about what we're physically doing with this thing, right? We want to calculate the change in phi over the change in x. Well, what do we mean change in? Well, what we're looking at is you're imagining that you're sitting at a particular point. Let's say you're sitting at this point, and you want to get the rate of change of phi. How much does phi change when you move along the x-axis? So what you're saying there is you want to leave y the same and vary x. So what you're looking at in terms of the grid is you're looking at going from this point on the left to this point on the right. And you're looking at how much does phi change by. Well, if I think about this in terms of the grid, what I'm changing here is I. I'm going from a lower value of I to a higher value of I, and I'm leaving j the same, right? All three of these points have the same j value because they're not moving in terms of y. So I'm going from the left. So I'm going from a point to the left to a point to the right. So if I think about this point to the right, the only index I'm changing here is I, right? I'm leaving j the same. So this is going to be phi I plus 1 j. Right? So if I leave y the same, so this is going to be j, and this is going to be I. So I'm going to say minus phi I minus 1 j. Right? So this is going to be the point to the right minus the point to the left. Right? So I'm taking the point to the right minus the point to the left. Now, there's other ways you could do this. You could take the point itself minus the point to the left. You could take the point to the right minus the point itself. The fact that we're doing this symmetrically, we're going to the right and to the left, is a little bit more accurate. That's preferable in this situation. In a few videos, we're actually going to have to do it differently, where we have to look at a point, and then the next point we can't look at the point behind it. But that's another topic for another time. And then we need to divide by how much our step size is. Right? So how much did we move along the x-axis when we went from here to here? Well, let's count it. How many ticks did we go? We started here. We went here. That's 1 step. Then we went here. That's 2 steps. So that's 2 dx's. So the distance we moved is 2 times dx. Okay. It's pretty straightforward to envision that, right? You're taking 2 steps along here, along the x-axis, so that's 2 dx. Every time you take a step, it's a dx. So wherever I have a first derivative, I can replace it with this. Now, Poisson's equation doesn't have any first derivatives, but you might have another problem someday where you do have one, in which case you'll need that. What about in the y direction? Well, in the y direction, it's going to work out the same way. When I want to move in the y direction, let's suppose I have d phi dy. Instead of looking to the right and looking to the left, now I'm looking at the point above, going down to the point below. Right? So in that case, it's not x that's changing anymore. Now it's y that's changing. Well, in terms of these indices, that means it's not I that's changing, it's j that's changing. So this is going to be phi, leave I the same, with a j plus 1, minus phi, leave I the same, with j minus 1, right? So this is now going from the point above to the point below. and you just divide by 2dx, because that's our step size. Okay. So it looks exactly the same. The only difference is whether you're changing I or whether you're changing j. And that's exactly what a derivative is, right? It's just how much the function changes by in the direction that you're moving. Okay, so that's the first derivative. What about the second derivative? It turns out you can work out the algebra to show this. In fact, I'll be releasing a video at some point about where this replacement comes from, because it takes about a board to show where it comes from. So it's not important for us today to see where it comes from, but I will show you where it comes from in another video. What you have to do is a similar setup. You basically have to apply this twice, right? Because the second derivative is the derivative of the derivative. And so you have to take this procedure and basically apply it twice. When you do that, you'll end up with this. So we're looking at changes in the x direction. So again, you just keep j the same and change I. So we're going to look at the point to the right plus the point to the left minus 2 times the point in the middle. Right? So it's a little more involved than these two are, right? This is a simple difference. This is more like you're taking the 2 points to either side. You're making both of them positive now and subtracting 2 times the middle point. You can kind of get an idea of where that comes from, because if I'm doing this twice, right, I need the derivative going to the right. I need the derivative going to the left. Since the derivative going to the left is backwards, that's going to flip the sign of this one. So that's how this ends up positive. And this one's going to always end up getting subtracted. So I'm doing 2 derivatives. So I have 2 of this thing. That's basically where it comes from. The other piece that changes, we're looking at our step size. Our step size is dx, but now our step size is squared. So this is going to be a dx squared down here. Again, I'll have another video coming out to show you where exactly this comes from, but you can kind of get an idea. It almost looks like a FOIL operation, right? So you have the first pair, the last pair, and then the outside and inside pair turning into 2 times the same thing, right? That's kind of what you can imagine there. And then when you want to do this in the y direction, you can have d squared phi dy squared. You can probably guess where this is going at this point. Instead of changing the I, you change the j. So you'll have phi of I to the j plus 1 plus phi of I with j minus 1 minus 2 phi ij. You notice that piece stays the same because that's always your center point, right? It doesn't matter whether you're going to the left and right, whether you're going up and down. That center point is always the same thing. The only difference is up here, you're changing I and leaving j the same. Down here, you're changing j and leaving I the same. And then we'll divide by dx squared, just like we had before. So in Poissons equation, where you have this del squared phi, where you have Laplacian phi, you just take this piece plus this piece. Okay, now that we've learned this recipe for turning all of this continuous stuff into discrete stuff that the computer can handle, let's learn the actual trick. So what we're going to do, we're going to take this entire equation, we're going to transform it into the i's and j's form that the computer can understand. So our del squared here of phi is going to be this piece plus this piece. So we'll have a phi to the right, phi I plus 1j, plus a phi to the left, phi I minus 1j, minus 2 times the phi in the middle, divided by dx squared. Now, both of these are over dx squared, and I'm adding them together here. So I can just go ahead and put all of those over a single dx squared. All right, so I'll have a plus phi above ij plus 1, plus phi below phi ij minus 1, minus another 2 phi ij. So I'll make a little note here that we're going to combine these on the next step. Right, because those both have a phi ij, is going to equal negative rho ij. And let's go ahead and put in our epsilon naught equals 1, just so we have one fewer things to write down here. When you want to work with real units, you just put in the actual value of epsilon naught. It's just wherever the rho is, it'll have a divided by epsilon naught there. It doesn't really show up anywhere else. So here's the trick we're going to do. We're going to solve this thing for phi ij. Because here's the thing, I want to solve for phi, right? My goal has always been to solve for phi as a function of x and y. That really means I'm looking for what phi is at each point on the grid. So we're going to take this whole thing, we're going to solve it for this phi ij. Now you might be scratching your heads and say, but I don't know what phi to the right, phi to the left, phi above, and phi below are. Don't worry about it. We're going to pull in another trick in just a second to work with that. But for right now, we're just going to solve for phi ij. Okay? So let's try getting that by itself. So I'm going to have a negative 4 multiplying the phi ij. Right? So I'm going to have a phi ij, negative 2 phi ij and negative 2 phi ij. It's being divided by a dx squared, but so is everybody else over here. So I can just multiply both sides by that. So we're going to take dx squared and multiply it over here. Right? So we'll just move it over there for right now. Let's see, what else are we going to be left with over here? We're going to be left with phi to the right, phi I plus 1j, plus phi to the left, phi I minus 1j, plus phi above, plus phi ij plus 1, and then phi below, plus phi ij minus 1. Right? So these four, they've always got to travel together, whatever happens in this equation, right? I've got the point to the right, I've got the point to the left, I've got the point above, and I've got the point below. Right? Now, whatever happens to one of them has to happen to the other, because there's no sacred direction in the problem, right? There's no reason that the above point should be treated any differently than the below point or the left point and the right point, right? Because these are all just the points around the central point, right? So these are going to kind of travel together as a group. So even though there's a lot of messy i's and j's in here, just think of these as kind of traveling as a group. So that whole thing has to equal a negative rho ij dx squared. So the dx squared just comes along for the ride. You notice this is the only piece that has a step size now, whereas before, it was underneath this whole thing. Now it's just nice and condensed down to the charge density over here. Okay, so I've got the thing I want over here. I have a bunch of stuff that I don't want over here, so I'm going to take all of this and sweep it over to the right-hand side. So I'll have a negative 4 phi ij going to equal, we'll just copy this whole thing with negative signs in front. Negative phi to the right, minus phi to the left, minus phi above, minus phi below. Then minus this thing here, minus rho ij dx squared. Oh, look at that. Everybody has a negative sign. So guess what we get to do now? We get to just cancel all those negatives. Okay? What's the only other piece left? Well, the only other thing I have is this 4 here. So we'll have a phi ij equal to, so everybody over here is going to get divided by 4. I want to write that a little bit differently. I'm going to group all of this stuff together. So I want to group all of these together. And then I want to group this separately, just to give you an idea of physically what's going on here. So I'll have a 1/4 times phi to the right, phi I plus 1j, plus phi to the left, phi I minus 1j, plus phi above, phi ij plus 1, plus phi below, phi ij minus 1. Plus over here, let's group all the constants together here, dx squared over 4, rho ij. Whew. Okay, I'm done writing all the i's and j's for now. So, here is the strategy. We're going to use a strategy called relaxation. This is one of those techniques that when I first learned about, I said, that's too cheap. There's no way this could possibly work. It almost feels like mathematically cheating, but it does work. Here's what we do. We're going to start with a guess for phi ij. Right. And you say, this is physics. We're not supposed to be guessing. Well, it works. Trust me. You'll see that it works in a few minutes. This is phi ij. We're going to start out with a guess. Right? The simplest guess is just phi ij equals a constant everywhere. Right? And what you do is you feed that guess into here, right? Because this phi ij, remember, this is an entire grid of values for phi. Right? So you have to imagine, when you see this phi ij, you have to imagine that from the computer's perspective, that it has a grid where it has a value for phi at each point in the grid. So what we're going to do, we're going to take this phi ij, we're going to feed it into this equation here. So we're going to feed that guess into phi to the right, phi to the left, phi above, and phi below. And what it's doing in this little equation here is it's saying that the point in the middle of all those 4 points should be equal to their average, right? So I'm adding up 4 things and dividing by 4. That's the definition of an average. So this whole first piece here is just the average of the surroundings. Right? Plus, this is the piece that messes that up, right? If rho were equal to 0, and we're actually going to start in today's video with rho equal to 0 everywhere, right? If you turn this off, if you say there's no charge inside the area, and you just start out with some boundary conditions, we're going to turn this off. Then it means every phi ij is just going to be the average. So you can loop over the entire grid. You can look at each point, look at the point to the right, to the left, above, below, and calculate a new phi based on that guess. So what you'll get there is a better guess. So this initial phi is a guess. This new phi over here is a better guess. Once we have a better guess, we can feed it back into the right-hand side. Then we get the average again. That gives us an even better guess. We take our even better guess, we put it in here, we get a super better guess. We take our super better guess, feed it back in, and the cycle just repeats. So the whole idea of this relaxation process is that you take your guess and you feed it back into the same machinery. And what the math predicts will happen is that this thing will level out to the correct answer, because only the correct answer is going to satisfy Poisson's equation, right? Because this is Poisson's equation, just turned from continuous into discrete. So only the correct answer is going to be stable here. And so after, a few hundred, maybe 1,000 go arounds of the loop, this thing will eventually get down to the guess that we want. Okay, so what we're going to do in the second half of this video is take a look at how the code works out in terms of setting up this guess, setting up our rho. Again, we're going to start out with rho equal to 0 so that we can just ignore this part for now. And then we'll look at how we set up this process of getting a better and better guess. And then in the next video, we'll take a look at what happens when we start to turn on the charge density. So in this Jupyter notebook, we are implementing our strategy for calculating the electric potential from boundary conditions. This file is available at a link in the description below. I've broken this up into several cells just so we can focus on one step at a time. Our first step is to just import all of the libraries that we need. You don't need to change anything about these. Then this is where we're going to define our charge density function. This, of course, is that rho that gets spliced up into those rho ij's that we saw earlier. Rho is a function of x and y, right? It can change anywhere in the grid that we're looking at. For today, we're just going to set rho equal to 0. So inside the region that we're looking at, we're not going to have any charge. So if you want to visualize it, we are looking at a square here. We've got x going along one axis. We've got y going along the other axis. And the charge everywhere inside is 0. The only thing we're setting up in this problem are the boundary conditions, right? So we're going to set a potential energy we're setting an electric potential at the bottom. We're going to set an electric potential along the left. We're going to set an electric potential along the right, and we're going to set an electric potential along the top. And those are the 4 things that are going to set for us the electric potential inside. Even though there's no charge, you have to imagine there's charge off somewhere else that's creating this electric potential boundary conditions, and then we'll get to setting those up in our next cell. So in the next cell, we're going to set all of the constants that we need and get all of our arrays set up. So the first thing we're going to do is determine how many grid squares there are going to be on each side. So if you just think about the x-axis, this is how many tick marks we're placing along the x-axis and how many tick marks we're placing along the y-axis. So the actual number of grid points is going to be this number squared. So you want to be a little bit conservative at first when you are setting this number, making it smaller just so that your code can run within the span of a few minutes as opposed to a few hours. When you want your code to become more accurate, you can increase this number, but I think you'll find you get pretty good accuracy just with 100 by 100 on the grid. Next, we're going to set our electric potential on the top, bottom, left, and right edges. I've just called this voltage here just because that's a shorter word than electric potential. So what we're going to do is set the top portion to have a potential of 1 and the bottom to have a potential of 1, and then we're going to leave left and right at 0. So we're placing the top and bottom at higher than the left and right are. These units don't really mean anything here. They're just here to give us, a sense of scale. Here we'll get our starting value of x and y and our final value of x and y. You probably won't need to change these. dx is our step size. You definitely don't need to change this calculation because that's always going to be the same. It's the range of values divided by the number of values that we have. And then here we need to create the arrays that are going to hold the values for the potential, for the electric potential, and for our list of points. So what we're doing is we're setting up phi. Our initial guess for phi is going to be 0 everywhere. That's fine. That's as fine a guess as any most of the time. What we're using here is NumPy's zeros function. So it's going to create a two-dimensional array for us, an m by 1 by m by 1 array of all zeros using floating values as opposed to integer values. And then we're going to do the same thing with phi prime, except this one's going to be empty instead of zeros. Just that'll store our next guess for the potential. You can set this to zeros if you'd prefer. It's just, now it's empty instead of zeros, but it has the correct number of empty slots that we need. And so these lists contain the xi and yj that we said we were going to split this up to. Then we need to actually set the boundary conditions. And in order to do that, we've got to access just the values that are on the left edge, the right edge, the bottom edge, and the top edge. So this is where we're going to use a little bit of Pythonese in order to do this. So this weird looking construction here, phi of 0, comma, colon. This means we're going to set everything in phi that has its first index 0 to be this value v left. So if you imagine this as a matrix, which is what it is, it's a matrix. You can always think of a matrix as being a grid of values. So you imagine each one of these dots is a value. So we're leaving the index for the row set at 0, and we're letting the column value here range through all of the values. So colon here just means isolate this particular slice along the matrix. Then down here where we get m comma colon, that's accessing the rightmost column. And then in the next one where we've got colon comma 0, now we're isolating the column value at 0 and we're moving along the possible row value. So that's getting us the bottom row here. And then for that last one, you probably guessed it, this colon comma m, this is allowing us to get the top row. And so those are the 4 pieces. Let me color code that red one just to be complete. There we go. So these 4 pieces, these represent the edges of the area that we're looking at. So you can kind of think of this as taking the physical geometry and encoding it as a matrix where the outermost rows and columns are going to represent the outermost spots in the region. So all of the stuff inside here we are free to change, but the rest of these are going to be left fixed at v left, v right, v bottom, and v top. We're going to skip over this next part for now. We will come back to that shortly. This is for if you want to set a function along an edge instead of a fixed value. That produces some great results we're going to look at in a little bit. Next is our target accuracy. This is just an idea of how accurate do we want the results to be. The smaller you make this number, the more accurate, the smoother the results are going to be. The larger you make this number, the rougher the results are going to be, but the shorter amount of time the code will take.
We'll see how this gets used in the loop in just a minute. So here's our main loop. This is where the actual numerical method takes place. The rest is just setup. Everything above this is setup. This is where the actual finite differences relaxation part takes place. So delta is keeping track of our current error. So target is our ideal error. This is our current value of the error. This one doesn't mean anything. It just needs a value so that the code will run. You just have to make this number bigger than this number. So, just make it a big number. It will change almost immediately. And so we're going to run this calculation. We're going to run our finite differences method until our actual error is less than our target error. So as long as we are not accurate enough, as long as our error, as long as our change is bigger than our target accuracy, we're going to keep repeating, right? Think of it like when you're turning in an assignment and your instructor keeps sending it back with comments for things for you to change, and then finally they give you a red check mark and you run home happy and put it on your refrigerator. That's what's going on here, right? So what we have to do is loop over the electric potential. So we're looping over every point in the grid. So we're looping over I, we're looping over J. You notice we're going to ignore the parts where we are along the boundaries, right? So the boundaries have to stay fixed. We are not allowed to change the boundary conditions because those are the things that are fixed. So here we're saying if we're on the edge, then you just keep that point fixed. We say phi prime equals phi. So phi prime is our new guess. Phi was our last guess. So phi prime guess is always going to be bigger than the phi guess. Otherwise, if we're on the interior, this is where we're going to use our difference equation. So all of the time that we spent in the first part of this video, this is the line that we get from that. The rest is just setup. This is the actual physics part. So we've got our phi prime of ij, our new guess, equals the average value of the phi's around it, right? We saw this earlier at the whiteboard, where we're going to take the point to the right, the point to the left, the point above, and the point below, and we're going to average those. We're going to add them all up and divide them by 4. The next piece is where we get the actual input from the charge. So this is where we have this dx squared over 4 that came in from all of the algebra that we were doing times the charge density. So we will get more into the charge density in our next installment. The only thing we're looking at right now is the impact of the boundary conditions. So this is the piece that is 0 for right now. So you can kind of just block this out in your mind for right now because that's always going to be 0 for this installment. And then we calculate the difference. Then we calculate how much the new guess changed from the old guess. Again, we're looking for the guess to steady out. So we want this value to be close to 0. That's that target value we were looking for. And basically what we're doing is we're taking all of the elements from phi and subtracting them from phi prime. We're going to take the absolute value because we really don't care which one is bigger, which one is smaller, because that's going to change depending on if they're positive or negative anyway. So we just put absolute value around that. And we're looking for the maximum value in that. So in other words, if all of the values match really well except one, we're going to pick out that one pair of values that doesn't match well, and that's going to be our error. So we're looking at the maximum difference between the old values and the new values. And then we just have to overwrite the new array, or excuse me, the old array with the new one. So we're going to overwrite phi with phi prime, and we might as well go ahead and swap them. This is a neat little swapping trick in Python. This is saying take phi prime stored in phi, take phi stored in phi prime. And so this part repeats. This is the main engine of the code. This is the thing that repeats over and over again. Then we need to get a graph up. So in order to do that, we have to turn x and y into a mesh. That's just a format that Matplotlib will use to graph our results. So we're going to call that capital X and capital Y. This is just a technical detail. You don't have to change anything about it. This is going to be our viewing angle for the graph. This is how we're going to be able to move the graph around and see different viewpoints. And then here we create our plot. We're going to use a surface plot to get our phi versus x and y. And we'll, let's see, we'll need to go back up here and run the first part. All right, so that took about 30 seconds to run, not too bad. So we go to our graph here. The first thing we want to check on this is the boundary conditions, because if the boundary conditions did not come out right, then we know something went horrifically wrong. So if I look at the bottom edge and the top edge, I see that I'm up at an electric potential of 1, and those are kept nice and constant there. And then down here at the right edge and the left edge, I see that my electric potential is kept at a constant of 0. So those are the sides that are glued. Those are the things that we set up at the beginning. And so what we're interested in, what we want to learn about how does this thing work, is what happens on the interior. We see we get some nice little color gradations here. I can see it falls down to 0 pretty quickly there. This is where that angle comes in handy, because let's say I want to get an idea of the profile of this thing. That's what this angle here controls. So I could change this value and then rerun the code, but then I'm having to recalculate all the data, go back over the loop again. Again, it only took me 30 seconds, but if I change the number of data points to where this takes an hour to run, I don't want to have to rerun it every time I want to get a new angle. And so that's why I've added in this cell here, where we can set a new angle and just reference the previous data, right? Because the data doesn't need to change. I just need to change the angle of the graph. So you can change your new angle here, press Control Enter, and you notice it gets me my result right away. So here I can see my profile here. I could even get a nice view on edge here if I change this other angle to a 0. So you can think of these as being your theta and phi in spherical coordinates. Thankfully, they are in degrees. Thank you, Matplotlib. So this is the profile that I get. So this kind of gives you an idea of what this thing looks like if you were just moving along the y direction. I could also get an overhead view if I put this in as, I think, 90. Yeah, there we go. So if I want to get an overhead view, this will give me a nice little color plot here. So here I get an idea of how quickly it gets down to basically 0. I can see that by about 8, looks like at about 7, I no longer see any noticeable changes in the coloration there. And so you can play around with the angles here. Again, I've got it in a separate cell so that you don't have to keep rerunning the calculation in order to just change the angle of the graph. And so you can go through and change these values. This is kind of the interesting part. This is where you start treating it like an experiment. So like I might change v bottom to a -1 and leave everything else the same. Oh, and you see here I've got this neat little S shape here, it looks like. Let's get an idea of what that looks like from let's go from this angle. Yeah, that's pretty cool. See how it gets really flat in the middle there because I've got 0 here, 0 here, and it's stuck between 1 and -1, which is pretty cool. You can also change the left and right boundary conditions if you want to. So like I might put my left up really high. Come down here. Yep, there we go. There's the left side winning out over all the others. Kind of washes everything else out there. Now, of course, these examples, all I've shown you so far is constant value, so a flat value along the edge. You could also imagine having a curved value, right? So maybe to make it nice and continuous. That's what this little chunk of code is for, starting in line 30. So the way this works is you can override these up here. So I still have these for the constant values, but if you want to override one of those and give it a varying value, let's say, for example, I wanted to change the bottom edge to be a parabola. So here is where we access the bottom edge is phi of a variable comma 0. Oh, I need to uncomment the for loop as well. There we go. Python will not like me for that. What this is doing is saying, okay, I'm going to go over index I, my x index from 0 to n plus 1. So I'm going to go over all of the x-axis. And I'm going to change all the values along the bottom. How do I know it's the bottom? Because I've got my j set to 0 here. And so the way we're setting this up is just as a parabola, right? A parabola is where the highest power of x is squared. You might have an x to the first power and an x to the 0th power. The rest of this is just here to scale it nicely. Speaking of scaling nicely, let's turn this back to 0 and this back to 1. And so this is going to override the bottom edge case. So instead of v bottom being 1, it's going to be this x squared business here. And there you go. See here I've got my flat boundary condition. Here I've got my parabolic boundary condition. Let's take a look at it from that side just to make sure that it's a parabola. So that's going to be a new angle of 180, I believe. Yeah, there we go. So and then let's bring this angle down a bit. So you can see by changing these two angles here, you can get whatever view you want. And you see there we get this nice parabolic shape along the along the bottom edge. And of course the advantage to that is it makes this edge continuous with the left and right edges, because I've designed this parabola in order to come down to 0. You notice I've got this huge discontinuity here along the top edge, whereas this one is nice and continuous. That's going to make the physics behave a little bit better on the inside there. You can see I get a little bit better behavior of the color shading here than I do here with this weird transition going up. And you can change that into whatever function you want. You can change it into sine or cosine. You can make it exponential. You could make it an absolute value, whatever you want. You could have a different function along each of the edges to get an idea of how they kind of meld together into the center. So that's an idea of how you can set these boundary conditions and get out your electric potential inside the region. There's lots to play around with these, all sorts of functions you can use. Next time we'll take a look at how this problem behaves differently when we start to add in a charge density into our region of interest. So thank you so much for watching. I will see you next time. Bye-bye.